Module 4, Lesson 5, Exponents. So taking a look at our learning targets here. Not going to see exponents specifically mentioned within any of the learning targets here. However, using exponents fits in with real-life situations, and as we are comparing the expressions are based off real-life situations, and we can experiment. So exponents fit into all of these that we're working on. In addition to, exponents have a relationship to the operations. So by the time we're finished with this lesson, hopefully you can show and explain that exponents are repeated multiplication, and you'll have some vocabulary that you have built: base, exponent, power, squared, and cubed. So take a moment and evaluate the following expressions, meaning figure out what they are. 7, 8, 9, 10. So I've got 10 times 4 here, which would be 40. That's one way I could do it, or I could add on. 4 plus 4 is 8, plus 4 more is 12, times 4 more, plus 4 more is 16, plus 4 more is 20, plus 4 more is 24, plus 4 more is 28, plus 4 more is 32, plus 4 more is 36, plus 4 more is 40. Here I've got 9 plus 9 is 18, 18 plus 9 is 27, 27 plus 9 is 36, 36 plus 9 is 45. We can also see this as 9 times 5 is 45. 10 plus 10 is 20, plus 10 more is 30, plus 10 more is 40, plus 10 more is 50. We've also got 10 times 5, which is 50. Now, as you saw, I evaluated the expressions using two different methods. I used repeated addition, so add the numbers together over and over again: 4 plus 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 4. And I also used multiplication. So one approach that people could use would be counting on. So you start with 4 and you count 4 more each time. And this is not something that I modeled, but I'll show it to you. So you start with 4, and then you go 5, 6, 7, 8. There's a second 4. 9, 10, 11, 12. There's a third 4. 13, 14, 15, 16. There's a fourth 4, and so on. So what are some advantages and disadvantages of counting on to simplify the expressions? Well, if you don't know how to add 4, if you don't know how to multiply, then you have to go back to simply counting on. So you can just keep counting on, even if you don't know how to add, even if you don't know how to multiply. Hopefully you've got fingers and toes and you can count on. One really big disadvantage here: it takes a long time to do this, and it would be very easy, if you're not concentrating or focused, to make a mistake. So adding on is what I first modeled. Add 4, then add 4 more, and then add 4 more. So advantage: if I don't know how to do multiplication, but I do know how to do addition, then this works okay. Big disadvantage: if we've got a lot of numbers that we're adding together, it can really take a while, and it increases the opportunity to make mistakes. So multiplication. Well, multiplication has some major advantages. It's a much faster way when we add numbers, when the add-ins are the same, if you know how to multiply. For example, when we add 5 groups of 10, we can use an abbreviation in a different notation called multiplication. So here's our repeated addition: 1, 2, 3, 4, 5, and here it is as multiplication. So that's a quick discussion of some advantages and disadvantages of multiplication. So if multiplication is a more efficient way to represent addition problems involving repeated addition, so multiplication is repeated addition, something that you have had pounded in your head for a long time. Is it possible that there is a way to show repeated multiplication in a simpler way. Instead of writing out all of those 10 plus 10 plus 10 plus 10s, we can write 10 times 4. Is it possible to write out something with repeated multiplication? And the answer is yes. We can write it out using what are called exponents. So here I've got 5 tens, and here it is written in exponential form in 2 different ways. Write those a little bigger so that you can see them a little more clearly. Both of these mean the same thing. So this is multiply 5 copies of 10. So multiply 10 together 5 times. So a quick look here at the parts of a number that are written in exponential form. Here's some of your vocabulary here. So the base is the number that we're going to be multiplying. The exponent is how many times to multiply. And sometimes exponents are also called powers. So to the power of 5. To the power of 5. So if we were to write this out as a multiplication problem, 10 is the number that we are multiplying, and we are going to multiply it 5 times. And this chevron symbol here means the same thing as that superscript. Notice when we write the exponent here, we write it a little small, and we write it up. This right here is an easy way to express exponents without using, this is called superscript, that little tiny there. This is writing exponents without using superscript. So a couple of examples here. Write each expression in exponential form. Pause for a moment. Think about how you do that. All right, 5 is the number that I am multiplying, and I am multiplying it 1, 2, 3, 4, 5 times. Now in some ways this is a really bad example because you can't really look and see the difference between the base and the exponent. Remember, the base is the number I'm multiplying, and the exponent is how many times to multiply. Example number 2 is a little bit better. Multiply 2, and we're going to multiply it 1, 2, 3, 4 times. Once again, notice with the exponent we write it small and we write it up. Writing it this way is a little more common when you're typing it into the computer. Usually when writing by hand, we will superscript it. So here's a couple other examples, and you can see that I'm starting to mix in the use of the chevron with the superscript. And we're supposed to write each of these, expanding them out and showing the multiplication. So 8 is the base, and multiplying it 3 times. So 8, 3 times. 10 is the base. It's the number I'm multiplying. 6 is how many times to multiply. One, 2, 3, 4, 5, 6. And here we're throwing in a variable. G is the number we are multiplying, and 3 is how many times to multiply. So taking a moment here and going back and looking at these first examples, 1 through 4, and actually finding the value of the expressions. And if you need to, use a calculator to solve these out and find the value. And there are some kind of cool little shortcuts you can do on the calculator, but won't get into those right now. One, two, three, four, 5 of them. gives me 3,125. And then 2 to the 4th, 2 times 2 is 4, times 2 is 8, times 2 more is 16. 8 times 8 times 8, 8 times 8 is 64, 64 times 8 gives 512. And 10 to the 6th, I'm going to think of that as 1 with 6 zeros. And then here is a thought question. What is the difference between 3g and g raised to the 3rd power? Pause and think about that for a moment. 3g means that I'm going to add g together 3 times. Whereas g to the 3rd means I'm going to multiply it together 3 times. And let's say that I picked 2 for the value of g. Well, this would be 2 plus 2 plus 2, which would give me 6. This would be 2 times 2 times 2. 2 times 2 is 4, times 2 more is 8. So they are definitely not the same. All right, so it says write the expression in expanded form and then evaluate. So we're going to write this out. And this is 3 8/10 raised to the 4th power. So 3 8/10 times 3 8/10 times 3 8/10 times 3 8/10. And once again, this would be a good one for the calculator. And that gives 208 and 5,136 10,000ths. And on this one, we're asked to write it in exponential form. Now, you can put the parentheses around the decimal just to be super clear, but you don't have to. You could write it like that. And that would give us 4 41/100ths. And here we've got 0 75/100ths, and we're raising it to the 3rd power. And that will give us 421,875 millionths. 421,875 millionths. It's an awfully lot of decimal there. All right, so the base number can also be a fraction. It doesn't just have to be whole numbers. And we're going to convert some decimals to fractions, and we're going to evaluate. So for example, 2 1/10 could be 2 1/10, and we would raise that to the 2nd power. Now there's lots of different ways to think about this multiplication here. Probably the easiest for what we're doing right now would be to take the 2 1/10 and turn it into 21/10 times 21/10. So we're going to get hundredths, and we've got 21 times 21, which is going to give us 441. And if we take that 441 and divide it by 100, we get 4 41/100ths. Here's a different example with a decimal. We can take this 75/100ths and we can turn it into 75/100ths. And hopefully your brain right about now is screaming at you, hey, isn't that the same as 3/4? I know my brain is screaming at me. So 3/4 times 3/4 times 3/4. 3 times 3 is 9 times 3 is 27. 4 times 4 is 16 times 4 is 64. So we wind up with 27/64. So we can use exponents with whole numbers, we can use them with decimals, and we can use them with fractions. So here we have an expression, and we're supposed to write it in exponential form and then evaluate it. So this would be 1/2, and it would be raised to the third power. And that's 1/2 times 1/2 times 1/2. Love ones, they're easy to multiply. And 2 times 2 times 2 is 8. So I get a value of 1/8. So a special name for numbers raised to the third power. Well, when numbers are raised to the third power, it is called cubing. Remember in geometry that cubes have the same three: length, width, and height, as long as b isn't 0. So for a cube, to find the volume of the cube, we would take the length, width, and height, and we would raise it to the third power. Remember, cubes, all the faces are exactly the same size. They're squares. So the length, width, and height are the same. Quick rough drawing here. So on cubes, this side right here is the same length as this side right here, is the same length as this side right here. Turn those into different colors here. There we go. So all the sides are the same length. So to find the volume of the cube, we take one of these sides and we cube it, raise it to the third power. So the value of 1 cubed, well, 1 raised to the third power is 1. Value of 2 cubed, 2 times 2 times 2 would give us 8. And the value of 3 cubed, 3 times 3 times 3, which would give us 27. So here we have an expression, and we're supposed to write it in expanded form and then find the value. So 2/3 times 2/3. Notice we're raised to the second power here, which would give us 4/9. So special name for numbers raised to the second power. Well, when we raise numbers to the second power, we call that squaring. So in geometry, squares have the same 2 dimensions. The length and the width are exactly the same, and usually they are expressed as the side because all 4 of them are the same. So to find the area of a square, we take the side and we multiply it by the side, or the length times the width. It's useful to look at it as side times side, though, because we see that the area is the same as side squared. Squares. So the value of 5 squared would be 25. 7 squared, 8 squared, and 1 squared. So doing a quick look at the multiplication chart, look for the square numbers and see if you notice anything. Go ahead and pause the video, take a moment and do that. It's interesting to notice that we have square numbers on the diagonals. So 12 times 12, 11 times 11. You'll notice these line segments that I'm drawing here are half of a square. Got 11 on this side, 11 on this side, which would make the other side 11 and the other side 11. So square numbers are diagonals on our hundreds chart. So is there a way to show what we know about exponents in a general form? So in other words, using some variables. Well, yes, there is. So we have the base, x, and we are going to raise it to the n power. So we're going to multiply it that many times. And we show that using a little bit of dot, dot, dot stuff here. So we have x times x, and we're going to keep doing that, multiplying x, and we're going to do that however many times n is. So that dot, dot, dot means continue doing this. So in this case, the x represents the base, what we're going to multiply. The n is the number of times that we will multiply. It's the exponent. So how would we represent 4 to the n power? So we're using that general form. How would we show that? Well, 4 to the n. We are multiplying 4. Now right there I stop at 2. Remember, we use these 3 dots to show that we keep going. And we're going to use the bracket here to say we're going to do this n number of times. So we would repeat this as many times as the exponent is. So picture the same thing right there. So in this case, the 4 is the factor, the number we're multiplying. The n is how many times to multiply. So if we're just multiplying, how would we represent 4n? So notice this isn't an exponent here. This is just 4 times n. Stop and think for a second. How would we show that? Well, using what we just learned with exponents, instead of making n an exponent, it's what we're multiplying by. And because we're multiplying, we are adding over and over again. We're using an addition symbol. So 4 is the number that we are adding. N is how many times to add it together. All right, so I'm not going to go through all of these, but your goal here is to fill in all of the missings. So we've got a variety of information, and you have to use that to build other things. So for example, on this one here, they give it to you in expanded form. You will need to write it in exponential form, and then you will need to evaluate it to put it into standard form. Use a calculator if you need to. All right, so we've got 5 cubed in all 3 forms: exponential form, expanded form, and standard form. So 5 is the base. It's what I'm multiplying. Cubed tells me multiply it 3 times, so there's my exponential form. Expanded form, 5 times 5 times 5. Standard form, 5 times 5 is 25, times 5 more gives me 125. So 14 7/10 squared in all 3 forms, so I would need to write it in exponential form, 14 7/10 squared. And I've got 14 7/10 times 14 7/10. So there is my repeated multiplication, which is the expanded form. And then we'd actually do the multiplication, and we'd come up with 216 9/10. So we've got standard form, we've got expanded form, and we have exponential form. So one student thought that 2 to the 3rd power was equal to 6. So they looked at this situation and they said, oh, that's got to be 6. So pause for a moment and think, what was their error? Where did they go wrong in their thinking? And how do you think you would help this student fix their mistake? Pause and think about that for a few minutes. This is actually a really common mistake for students to make. They look and say, oh, this is 2 times 3. So they take the base and they multiply it times the exponent. Well, the problem with that is we're not doing 2 times 3. We're multiplying 2 3 times. So this student is clearly not understanding the significance of an exponent. They're not understanding that this is how many times we will multiply, not how many times we will add. If we wanted to add over and over again, we would do 2 times 3. All right, so we use multiplication as a quicker way to do repeated addition if the add-ins are the same. We can use exponents as a quicker way to multiply if the factors are the same. That's kind of an important qualification there. If we're multiplying a whole bunch of numbers together over and over again, we use exponents. It is important that we write our exponents carefully so that we don't confuse people. I can't tell, is that supposed to be 2 times 3 or is that 2 to the third? So once again, we put the base here, we bring that up here. You'll kind of notice an imaginary line here. I try to get my exponents nice and high so that I know that they're not sitting down here in a multiplication spot. And they're not looking and saying, hey, it's 23. I want them to know it's 2 to the third power. So quick look at lesson summary here. Exponential notation for whole number of exponents. So m is a non-zero whole number. And for any number a, which is the base here, a to the m is the product of m factors. So in other words, we're going to multiply a together m number of times. The number a is called the base and m is the exponent or power of a. When m is 1, the product of one factor just means keep the same number. So a to the first power is just a. 5 to the first power is just 5. Now, raising any non-zero number to the power of 0 is defined to be 1. So for example, if I've got 5 to the 0 power, that's 1. 0 to the 0 power does not get to turn into 1. That doesn't happen. That doesn't happen. All right, so a quick review of some I can statements. Show and explain exponents are repeated multiplication. And hopefully you are familiar now with the vocabulary of base, exponent, power, squared, and cubed. Quick look again at our learning targets here. Working with exponents is really going to fit in through pretty much everything in our learning targets. So go ahead and work on your problem set. If you've got questions, make sure you talk to your teacher about them. And that concludes this lesson.